Okay, so today's really an honor for me to introduce our speaker, Professor Warner. I think the very first time I met him, or at least was in his presence, was in a seminar setting like this, but it was at Wayne State University when I was in graduate school. And he's a very distinguished professor. In fact, if you look at the bio, he's a vice president for strategic initiatives at Louisiana State University. He's also the Philip West Professor of Chemistry, the Boyd Professor, and HHMI, which stands for Howard Hughes Medical Institute Professor. I think that means you are funded. Isn't that what it means?
That means that I was funded at one time.
At one time? Okay.
Yeah, there are still some benefits we get from that, and it is a continuing society, but
okay.
They then tend to transfer the funding to a younger group of scientists, but we all continue to participate in the society.
Okay. So he's been in, this area of working in the area of fluorescence spectroscopy for the last 35 years or so. The research he's going to talk to us is fairly recent, I believe. He gave it the name GUMBOS, which is kind of significant, a play on the fact that he is from Baton Rouge, Louisiana. In addition to his research, reputation for research, he's also very active in trying to enhance the diversity of the workforce in chemistry and in science in general. And he's received, for example, a recent award, fairly recent, 2014, the Stanley Israel Regional Award for advancing diversity in the chemical sciences. He has over 350 publications and book chapters, and he has chaired over 60 doctoral students. So it's an honor and a privilege to have such a distinguished educator here with us today. Thank you very much for accepting our invitation.
Thank you for the invitation. This area of research is something that is really a spinoff of other research I was doing probably 10, 12 years ago. And I'll introduce that other research, which involves ionic liquid chemistry, and then explain to you how it drifted me off into this other region of materials research. So the title is GUMBOS Research with QCM Technology, and the QCM stands for Quartz Crystal Microbalance. And I'll explain what that is in a little while. But first, let's talk about ionic liquid chemistry. Ionic liquid is basically defined as an organic salt with a melting point less than 100 degrees C. And just this year is the 100th year of the discovery of these kinds of materials. And this is an example of the first material which was discovered to be an ionic liquid, because when we think of salts, we tend to think of solids. When we think of sodium chloride and many other salts, even organic salts, they tend to be solids. But just as the name implies, these materials are really liquid, which makes them somewhat unique. And here are examples of different counterions that are often used to make ionic liquids. On the left, we have the cations, and on the right, we have the different anions. And you compare any of those, and typically you will get a liquid or low melting solid. And sometimes, I mean, there's an extensive list of these, and these are just examples. For example, if we look at hexafluorophosphate, that's just one kind of phosphate. Here are a bunch of other phosphonium cations. that are used. In particular, the one in the top left corner called P6614, it is sometimes referred to as a universal liquefier. And the reason is if you take an anion and pair it with that cation, you will almost always get a liquid or certainly a low melting organic salt. And so there's obviously a whole variety of these molecules that can be constructed. In fact, someone has estimated just for ternary ionic liquids, there are about 10 to the 18th different varieties you can synthesize. And go beyond that to other kinds of ionic liquids. I mean, the number and magnitude of these is just mind-boggling. So here's the one that we refer to as universal liquefier. Now, when we think of salts, as I indicated, you think of something like sodium chloride, which is neatly packed. And so because of its neat pack into a crystalline lattice, these things tend to be high melting. So you have the chloride and the sodium complementary form these lattices. And so sodium chloride has a melting point greater than 800 degrees C, I think something like 803 degrees C. But in the case of ionic liquids, you want them not to pack. You want irregular shaped molecules that cause them not to pack regular, and therefore they will be low melting materials. And that's the whole idea of this. And why would you be interested in these low melting salts? Well, here's some of the properties of these. They're non-volatile. So we think of our current problem now with the atmosphere, where we are causing a problem with global warming, right? Because a number of materials like organic molecules will drift off into the atmosphere and interfere with the ozone layer. If these things can be used as solvents and they don't volatilize, they will not create that problem. So they're sometimes referred to as green solvents for that reason. They have high thermal stability. That's unusual for an organic salt or any organic material. Organic materials, for those of you who work in laboratories, know that if you heated them up too high, well, let's say with a burner, they will tend to char. These materials are less susceptible to those kinds of problems. They have high ionic conductivity because they're made of ions. That makes sense. They are highly solvating. They're good solvents of many organic and inorganic materials, and you can make them hydrophilic, hydrophobic, and these kinds of properties can be manipulated simply by changing the counterion, which makes it very interesting. They're recyclable, and therefore there's a reduction in cost. In other words, I can use them for one application, recover them, and use them again. They're tunable, as I indicated earlier. You vary in the counterion, and you can change the properties. And I'll give you some examples of that in a minute. Here's an interesting application. I mean, these systems are so unique, you can form triphasic systems. I doubt if you've seen that with any other system. On the left, you have the ionic liquid at the bottom, the water layer in the middle, and the more organic phase heptane at the top. Or if you want to reverse that, you use chloroform, and chloroform will be at the bottom, the ionic liquid in the middle, and the water at the top. Now you can think of a system like that being employed for some very useful chemistry, like solvent extraction, or you could, for example, have a reaction in one phase, and then the products being pulled out into another phase, driving the reaction forward in the appropriate direction. So there are all kinds of ways that these kinds of chemistry can be used. There are so many applications of ionic liquids that I just gave a few examples here. I mean, they're used in pretty much every area of chemistry and engineering that you can think of. These are just a few of the examples as I indicated. I'm not going to go through them, but if you were to look up ionic liquids, there would be an enormous number of applications. So recently I wrote an article where this was a couple of years ago, where I talked about my more recent research of using that ionic liquid chemistry in terms of manipulating materials chemistry. In other words, I'm going to make materials whose properties I can manipulate simply by changing the counter ion. And that's what this article was about. I gave a number of examples of how this chemistry can be used, including the one I'm going to talk about more extensively today. So, where did the name GUMBOS come from? GUMBOS is simply an acronym. It stands for a group of uniform materials based on organic salts, GUMBOS. So being from Louisiana, I wanted to come up with some name that would be recognized as a Louisiana type name, and clearly GUMBOS is a name that's very much affiliated with Louisiana. And they're solids with tunable properties similar to ionic liquids. That is, I can tune the melting points, the functionality, etc. Now I'll give you some examples. And so here's just a chart to show you that ionic. Now some people have said, why don't you just call them ionic liquids? Well, I can't, because my GUMBOS have a melting point between 25 and 250 degrees C. They're solids, whereas ionic liquids are defined as less than 100 degrees C. And it's not up to me to change the definition of ionic liquids. And so I wanted my materials to have a more expansive range beyond. Now, between 25 and 100 degrees, obviously ionic liquids are solids, but they're low melting solids, so that's consistent with the ionic liquid definition. But I wanted to expand outside of this range, and so I had to come up with another name other than ionic liquids. But when people hear about my work, they're simply saying, you're doing ionic liquid chemistry. Well, to some extent, that's correct. But to another extent, it's not correct, because I am using these counter ions to go beyond the normal melting range of ionic liquids. Okay, for some reasons, okay. All right, here are a number of examples of these kinds of applications we've done. We've created materials that are initially toxic to both normal and cancer cells. When we convert them to GUMBOS, they're toxic only to cancer cells. And we have a number of papers on, at least a couple of papers out on that, another one about to come out. We've done magnetic liquid extraction using ionic liquids. We've developed new kinds of organic light emitting diodes, new kinds of materials for OLEDs. We've developed sensor arrays and liquid crystals and dyes or electrolytes that can be used in solar cells. So the applications are enormous. And we think we've just touched the tip of the iceberg. We think the number of applications will go far beyond what we've seen at this particular time. So let's talk about today's talk, QCM-based GUMBOS sensor, detection and molecular weights of volatile organic compounds. So we published a paper in the Journal of Materials Chemistry a few years ago, and that was on this work a couple of years ago. And what we talked about was molecular weight sensing properties of ionic liquids. We were the first to do this. No one had ever thought that the quartz crystal microbalance could ever be used for determining molecular weight. And I'll explain why, and I'll explain how we were able to achieve this. So the young man who published this work is Dr. Vishnu Regmi, who has gone on now to do a postdoc, and also Dr. Nicholas Spellis, who is also a bright young man who's doing a postdoc now at Georgia Tech. So we've done a number of bioanalytical sensor applications involving these determination of freshness of fish And meat could be one application of this. Discrimination of bacterial species, diagnosis of diseases, analysis of breath and urine for cancer biomarkers. Any volatile species that can be induced to adsorb to a surface can be used for quartz crystal microbalance. So how do these sorption-based sensors work? First of all, you got to have a sorbent layer that is some chemically active coating on the surface. You have to have some kind of transducer that converts the binding event of the volatile materials into an analytical signal. And then you need some simple, compact and device that's amenable to creation of sensor arrays. So this is just an example here of what I'm talking about. The red stars are the volatile material. The yellow is obviously the chemosensitive coating. And the grayish blue is the transducer. I assume it's grayish blue. My wife tells me I'm colorblind, so it looks grayish blue to me. So piezoelectricity is one kind of transducer that's quite often used. And I'll explain to you the piezoelectric effect in a minute. But the converse of the piezoelectric effect also can be used, and that's what we're using for the quartz crystal microbalance. And here are some examples of piezoelectric materials. In our particular application, we're using quartz. So how does this work? Well, if you piezoelectric materials, if you apply a voltage to that material will be stressed and it will compress. If you apply sinusoidal voltage, as we're doing here, that material will vibrate. And it will vibrate according to the frequency of the voltage that's being applied. And it turns out that vibrational frequency, if you add a particular mass to that material, that vibration will be dampened. And the amount that vibration is dampened will be proportional to the amount of mass of material excuse me, of the amount of material you've added to the surface. Excuse me while I take a glass of water. And so many years ago, a scientist by the name of Sabray figured this out. And what he found was that shear waves produce a phase shift and attenuation at the interface when you add these materials. This phase shift causes a frequency change, which depends on the mass of material that you added to the surface. And so he came up with this equation that delta F is equal to minus a constant CF, and you can see the terms here that CF depends upon, times the change in mass. So for hundreds of years, this material, this particular device has been used, I shouldn't say hundreds of years, probably more like 60 or 70 years, but 60 or 70 years, this material, the quartz crystal microbalance, has been used simply as a means of measuring the mass of very small amounts of material. And that's all it's been used because that's what the Sabray equation says. That is simply proportional, the change in frequency is proportional to the change in mass. Now, there are other parameters associated with this, such as delta R, and delta R is the attenuation and motional resistance change, whereas delta F is the frequency change, right? And so delta R is hardly ever used. I mean, you can look at some papers in the literature, they'll use delta R, and it's mostly just a qualitative use of that particular parameter. R is the resistance of the equivalent RLC circuit for the crystal and how that crystal vibrates. R is less well-defined than delta F. There's no exact equation as you have with the Sabra equation. And thin and rigid films, what they've observed, exhibit less dissipation and hence a small increase in R, whereas thick and viscoelastic films exhibit high dissipation and therefore a large increase in R. So here's the quartz crystal microbalance. Top view, just the yellow is just the gold surface, and the bottom view is also gold. And in between we have, over to the right, the crystal sandwich between those gold surfaces. And the crystal, as I indicated, using quartz crystal microbalance is typically quartz crystal. And so you apply that voltage on those gold electrodes, and you apply the sinusoidal voltage, you get the vibration that I talked about. And so we bought a simple QCM instrument. I think we maybe paid a couple of $1,000 for this particular instrument. It's very inexpensive. And we started doing some studies with this. And what we did was we built a chamber in which we could input argon gas, and at the bottom of that chamber is a piece of filter paper with a volatile gas. And so we can volatilize that material and then measure using the head of the QCM at the top. We can then measure the change in frequency. And so in doing that, and this is what the surface looks like on that particular crystal. So we put different ionic liquids on that. You'll notice that these are different ionic liquids with different cations. Well, I'm sorry, this is same cation here, but different different thicknesses. And so we use laser scanning confocal microscopy to get these images of what the surface is like. And so the surface is 2.6 micron, 2.8, and 3.2 micron. Those are the maximum height on these particular materials. And what my student noticed was, he came in, he tested various gases. And he came back and he said, Dr. Warner, it's interesting that I get different slopes for different gases. And he said that if I look at the concentration, some gases are more sensitive, others are less sensitive. And others probably had seen this in years before, but they had not interpreted it in the same way that we interpret it. And when he showed me this, that it was very much dependent upon the, in this particular case, we're talking about different concentrations of acetonitrile. Where is it? Okay. And what he showed me was that different slopes would be exhibited for different gases. And so I asked him to plot the sensitivity versus the amount of coated material. And as you would expect, there's a linear relationship between the sensitivity of the quartz crystal microbalance and the amount of coated material. And again, this is for various concentrations of acetonitrile as detected by that particular liquid. And the response was very interesting, because for our particular material at the top, where you have 176 micrograms of material, that was the linear relationship. And down, if you look at the bottom, where you just look at the ionic liquid and the other material, this is what he did was he made a mixture of cellulose acetate. And the top one is a composite of cellulose acetate and the ionic liquid. The other one that has a curve is simply the ionic liquid, and the bottom one is the cellulose acetate. And you notice when we have the composite, the sensitivity increases and it becomes linear, which was very interesting. And we were able to explain this. I'll explain it to you a little bit later. The other thing was, if we plotted delta F and we plot delta R is the curve in red, and delta F is the curve in blue or black. And you notice that they are going opposite directions. But they do respond, they both respond to the amount of material. The intensity is proportional to the amount of material. And so both R and F respond to the amount of material. If this is not our system, but notice here are over the time frame here, time per minute, this is the kind of response that other people would get. You will never reach a plateau. Whereas if you look at ours, we reach a plateau in a very short time period. These are in seconds. Whereas one that we obtain from the literature, these times are in minutes, and they don't reach a plateau. So that says the response of our material is very rapid, and it clears out very rapid. So here's a direct comparison of our system in seconds and another quartz crystal microbalance system, and the response there is in minutes. Clear that our system is superior in terms of response time and in terms of deabsorption of the particular material. So here's what he observed, where he looked at the change in frequency as a function of different materials. He said the slope was very much dependent on the material used. I said, that's very interesting. And he said, I wonder why. I said, I don't know why, but let's try this. Let's try plotting these kinds of materials. And we're going to plot delta F versus delta R. And again, he noticed that delta F versus delta R depended on the slope that you obtain, very much dependent on the material that you use in the gas phase that you're detecting. And again, why is that? I said, well, try one thing. Plot delta F over delta R versus molecular weight, just out of curiosity. For some reason, there was a gut feeling to me that maybe this has something to do with molecular weight. Just do that plot. And when he did that plot, he got a linear relationship with an R square of 0.99, which is an incredible correlation. So delta F over delta R was related to molecular weight. So the question that we raised, how can this be true? Well, let's examine that. If delta F over delta R is related to molecular weight, we know what delta F is related to, right? Delta F is related to the mass of the material. Well, how can you get molecular weight out of that? So delta R then must be proportional to moles, or the number of molecules. How can that be? Well, if we go and look at delta F over delta R, again, we know that delta F is related to mass absorbed, and we're assuming delta R is related to the number of moles. Then what we get is delta F over delta R is proportional to the molecular weight of absorbed species. That's the way that relationship would work. And so delta R is telling you something about the moles of material, whereas delta F tells you about the mass of material. We found that to be very interesting. So equation 3 implies the following, that we're using all of these different gases. So they must behave essentially as ideal gases. Otherwise, this relationship should not be true, right? Because we're getting something that is a parameter, which is an ideal parameter, the molecular weight. And so in order to get the molecular weight of these individual gases, these gases must be behaving in a manner very similar, such that molecular weight comes out of that. So our materials respond ideally to each volatile organic compound. If so, then delta R should be independent of the volatile organic material. In other words, if I did a plot and I were to plot all of these organic gases, they should fit the same line. Thus, a plot of delta R for all gases should fit the same line. And indeed, that's true. Notice that at lower concentrations, fits much better. At higher, you get bigger deviation, which is what you would expect for ideal gas behavior, right? Gases, as you get the higher concentrations, these gases interact with each other, and therefore you get deviations from ideality. Lower concentrations, they do not interact with each other, so you get better fit to ideal gas behavior. And this is simply a plot of delta R versus nanomoles for all of these volatile organic gases. And notice that you have an array of gases. We have methanol, acetonitrile, ethanol, acetone, propanol, so toluene, which is a benzene-like chloroform, tetrachloromethane. So we have a different, a variety of different gases that follow the same law. Now, what we eventually found out, if you go to high enough concentration, you do indeed get deviations from ideality, and you get this curvature. And then we found out, we figured out that molecular weight must equal to delta F over some term delta R squared plus K times delta R. And so at low absorbers, delta F over delta R is equal to K times the molecular weight. So in fact, it's a nonlinear term in R, but at low concentrations, we get this relationship. So if we use a different composite material, you still get that linear relationship, and you still get the delta F over delta R relate to molecular weight. So it's not just unique to the particular composite that we use. There are a number of different materials which will give you this molecular weight information. And the properties that are required is that the material must be viscoelastic. Viscoelasticity means that if you distort the material will come back to its original shape and form. And I'll show you an example of what I mean. Viscous ionic liquids or ionic liquid composites. And the reason we initially observed this is that this composite of cellulose acetate and the particular ionic liquid we use gave a very viscous material. And viscosity is a very important part of it. And here's what viscosity is. If you expand the area of material, that material will shrink back into its original area. If you apply a shear force, if you take that shear force away, it will come back to its original. If you bend the material, it will come back to its original shape. And that's the properties of a viscoelastic material. It tends to retain its shape. There are plastics, for example, that are viscoelastic. If you press very hard into these plastics, you might form a hole into these plastics. And these materials will eventually come back to their original shape and will eliminate that hole or that indent into the material. Those are termed viscoelastic materials. I'd like to thank my research group, who are, these are the people that were involved in some of the research here, but all of my GUMBOS research, these are the folks that are involved. This is an old slide. We need to update our slide. Particularly, I'd like to thank Vishnu Regmi, as I indicated, and Nicholas Speller, the two students who did the bulk of this work. And also the National Science Foundation for supporting this work. I'd be glad to answer any questions you might have.
Associate Cadre first. Okay.
Hello, my name is Kadra. I noticed in the first slide that, well, not the very first slide, but for the ionic liquids, you used phosphorus as the central ion. Was there a particular purpose for that? Was it for biological applications or?
No, it turns out that phosphorus is easy to manipulate it and to get a variety of different ions. And so you can manipulate that chemistry and substitute different kinds of materials on there to give you a cationic species. So that's why it's used. And it turns out that people have done, in other words, I'm taking advantage of the chemistry that's been used for ionic liquid chemistry. And so they've done this kind of chemistry and figured out that phosphorus is a good ion to use to impart certain properties to these counter ions.
My name is Michael, and my question is, in what field would the best use of viscoelastic materials be practiced? Like what industry?
Oh, well, we just got a proposal funded for $1.5 million where we're going to study viscoelastic materials for looking at, for example, NASA sends out a shuttle, let's say out into outer space. And let's say the shuttle is made out of metal. And you have a meteorite comes in and knocks a crack into that metal. Well, if instead of making it out of metal, you make it out of viscoelastic material, the meteor hits the shuttle made out of plastic will begin to heal itself, right? If it's viscoelastic, the material will try to recover back to its original shape and form. And so you have a self-healing type material. That's one example of how this can be used.
Hi, my name's Don. My question is, how long does it take the GUMBOS to determine the molecular weight of something? How long does the test take?
We can do this test in a few minutes. I mean, tens of minutes, in less than 15 minutes, we can do a molecular weight. Now, this is with our current setup. Eventually, you can envision developing a strategy that will make this much faster. All things during the initial discovery are very slow. And then you begin to think about how can we speed these things up? And I can envision being able to do this in less than 5 minutes.
Hi, my name's Victoria. So I think mine's sort of a continuous question. So it seems like you have a lot of different types of research or a lot of specifics undergoing like your broad topic of GUMBOS. So then what's your next step in your research, or like where do you hope your research will eventually go towards?
Well, actually, one of the problems that we're having is that it's taken us in so many different directions that people are thinking that, oh, you've been playing with these GUMBOS for a while and you're really not doing anything with it. Well, it turns out that everything we try with these things sort of has, I mean, it's like the Midas touch. Everything we try really works. To give you an example of making nanoparticles out of it, out of a material that originally kills both normal cells and cancer cells. When we make it into a GUMBOS, it only kills cancer cells. And we just figured that out why that happens. That's one area. Another area is for solar cells. We made a material which is an organic salt that has properties that may potentially provide solar cells with efficiencies better than 50%. And currently we're limited to about 20% efficiency in terms of solar conversion. And so other materials have had similar properties, but they're all very toxic metals. This is the first example of a material where we can use an organic salt that has a similar property to these metals. We've created new kinds of compounds that can be used in organic light emitting diodes, where we can have very stable material. Many of these materials don't decompose until they're much above 300 degrees C. So you can see where these can be used in new kinds of television screens. I mean, every application we've tried has just really turned out to be so fruitful that one student will pursue that. And we're waiting for the one big application that we'll all concentrate in. And then I think people will begin to see the utility of our work. Right now, because we're in so many different areas, different people are seeing our particular work, but it's only a small impact in each of these areas. Whereas they saw the aggregate of all of our work, I think they'd be very impressed.
Hi, my name's Dylan. Going back to the viscoelastic material, I imagine there's a point where there's too much shear or too much puncturing and the material gets fully damaged. My question is, can the material be put back together and self-heal, or does it have to be reprocessed?
It will likely have to be reprocessed. You're right. There is a point at which if you do too much damage, the material will not be able to come together. And the idea is that this will satisfy for minor punctures.
Hi, my name's Gabriel. I saw earlier that you had on your application slide, you said that gumbos could be used for moldy matrices. I was just wondering, how would these materials be better than the current materials?
Well, we're doing some studies right now. That's another area that we've used these studies on. We've used them as additive to molded materials in that they improve the efficiency of many materials that are currently being used. And so they can be used in addition to the normal materials. And you can get, the other advantage is you can tailor these materials to particular hydrophobicities or hydrophilicities. And so you can get selective molding of certain types of compounds. We're using that now in imaging, brain imaging, for example. If you want to look at certain peptides, we can make a GUMBOS material that will have a particular hydrophobicity and will extract out a certain particular group of peptides. Again, this is just at the beginning, but we're seeing some very exciting and fruitful results.
Hi, my name is Cleve Hines, and adding to what Michael and Dylan said, a question they asked was that when the material was damaged, if it will come together and fix itself, and it can damage to a point where it has to be reprocessed. Yeah, I got that. Now, my question is, this material can be used in machines and airplanes and cars and so on. Is the material heavy, or is it way less?
It's an organic polymer, so it'll be very lightweight.
Okay.
And you have to understand that this is just the beginning. We just got, as a matter of fact, we haven't done any work using this award. We've just gotten this grant just within the last month, and it's still being processed through the university. So we haven't done any research yet, but it will definitely be lightweight material because it's made out of organic materials.
Other questions? Oh, yeah.
Hi, my name is Yewan. I saw
at the beginning of your presentation that you said that there's like a breath test for the detection of cancer. So
Yes.
what exactly in the breath is it that you guys are looking for that can help detect cancer?
That is not work that we're doing. What I'm saying, that's a potential area of use for our work. If you look in the literature for breath tests for cancer, you get some volatile compounds out that are representative of cancer. Let me use another example, diabetes, right? When you're diabetic, if you're not controlled, your body generates these compounds which are very toxic. And these compounds come out in your breath. So you can certainly detect diabetes, and you can see if cancer cells are being created in the body and they behave very differently than normal cells. They will generate species, which may come out in your blood and ultimately in your breath, which will be indicative of that kind of cancer. People have shown that these kinds of tests do indeed work. We haven't done any of them. I was just showing you an example of how something like a quartz crystal microbalance might be used.
Hi, this is Dylan again. I might have missed it in the very first part, but I remember you referencing a triphasic material.
Yes.
And I was very curious how, in one instance, you put the chloroform first and then the water. But then when you did a different combination of the materials, it appeared that they went into different layers. So I'm kind of curious of the mechanism of how that works, because it doesn't seem to be strictly polarity if you can get different combinations based on what order you add the materials.
It probably is a combination of polarity and maybe density. So it's a combination of different kinds of things. And certainly insolubility also, right? You have to have these material not be miscible in order to get those three phases. And the interesting things about ionic liquids is you can make ionic liquids that are very selective in terms of their miscibility. For example, there are ionic liquids that are essentially insoluble in water, soluble in methanol, and insoluble in hexane. So you can have that kind of selective solubility. So it's all of those things that are not consistent with traditional chemistry, which allows you to do those kinds of things. Many of these things, you think about them, it contradicts what we learn in chemistry.
Thank you.
The other example I like to give is that you can make an ionic liquid which will selectively dissolve certain things that can't be dissolved any other way. Like there are ionic liquids that allows you to dissolve cellulose. You can't find very many solvents that will allow you to dissolve cellulose. But there are ionic liquids that will readily dissolve cellulose the same way water will dissolve sodium chloride.
Okay, so I think we have exhausted the questions here. I guess from what you've described, your Office of Development and Commercialization has a lot of work going on, Cattington.
Yeah, we have about 3 or 4 patents pending in this area right now. I've lost track, but they're pending. We don't know if we'll get them, but they're pending right now.
Okay, well, thank you again very much.
Okay, thank you all, and I'm really happy to visit with you in this matter.
Okay. We gotta get some grants, man.